All right, so our last big topic we're going to talk about is incomplete block designs. I wanted to just mention the idea of the block is completely generalizable. So you can have a randomized complete block design where you just have one block, but it's completely the treatment levels are completely randomized to each block, so you have complete replication of all treatment levels within block. You can also do that with Latin square. There's also these things, other kinds of block-based designs out there. It's kind of just more of the same over and over. I think it's more useful to move on to incomplete blocks instead of just kind of seeing similar but slightly tweaked designs over and over again. Hopefully after this introduction, it should be clear to you in a given scenario which of the different blocking designs, if you have complete replication of all treatment levels within a block, which one you should be using. So instead, I want to move on to incomplete blocks because this is really important and something that happens all the time just because of physical and space and time and other limitations that have to do with real life. Okay, so complete blocks like randomized complete block and the Latin square, again, like I just said, have every single treatment level occurring in every block. That's great when we can do that. But sometimes we only have K units within a block and K is smaller than G. So remember, G is our number of treatment levels. And so if we only have K units within a block, we obviously cannot completely replicate all treatment levels within a block. So in these cases, we need an incomplete block design. So think about scenarios like this. 3 different eye drops are being studied to test relief from irritation. There's only there's a lot of subject to subject variability, so this would be, people respond differently to these eye drops, as you might expect. So we need to block on subject, but I think we all know we only have 2 eyes, each of us. Maybe a few have 1 eye, but at most we have 2 eyes. And so we'd have trouble replicating every single of the 3 levels for our treatment of eye drop formulation on each subject. So this is inherently an incomplete block design. Similarly, we have 6 different processes for extracting avocado oil. There's a lot of variability in the avocado oil content when you look from fruit to fruit. But each avocado is only large enough to test 4 processes rather than the full 6 replications. So again, incomplete. So incomplete block designs are going to be less efficient than block designs, but we have to do it this way. I mean, we just saw 2 examples where we don't have a choice. We have to have incomplete replication. So for example, if you have 3 levels, A, B, and C, this could be like the eye drop example. If we had complete block, we'd want those all to be replicated. But again, a subject doesn't have 3 eyes, so we can't do it this way. We have to do it this way. Okay? So notice we do get replication of everything. And notice A appears 2 times, C appears 2 times, B appears 2 times, but it happens within 3 research subjects rather than 2. So it's just less efficient. In the complete block, Unit 1 and 2, Unit 4 and 5 both estimate A minus B, but in the incomplete block, it's a little bit more complicated, more or less. Okay, we prefer complete blocks when we have equal variation between, or heterogeneity between the complete and incomplete, but often we see that that heterogeneity is bigger for the complete than it is for the incomplete. And so this is actually a place where using incomplete blocks might actually be a choice rather than a forced option. So let's think about, again, that avocado example. Suppose fruit-to-fruit variance in oil concentration is 10, but quarter to quarter within a fruit variance is 1. Okay, so this makes a lot of sense. If you pick up a few avocados, we might expect a lot of heterogeneity in oil content. But within a particular fruit, that heterogeneity may occur according to location of the fruit. There may be differences, but it's going to be far, far less than the fruit-to-fruit oil concentration heterogeneity. So the relative efficiency of a incomplete block design with 6 treatments of blocks of size 4 is 0.9. Without blocking, the variance of a pairwise difference in means is just going to be that 10 times 1 over n plus 1 over n, so 20 over n. But with an incomplete block design, we can incorporate this relative efficiency, and we get a reduced variance for pairwise differences. So this is a case where that incomplete block, this BIBD, by the way, is the acronym for a balanced incomplete block design, where this incomplete block design is going to be a better way to control the variance of our pairwise difference between the means. So here we do have a loss of relative efficiency when using an incomplete design, and you might have to have more research subjects because of that loss in relative efficiency, of course, but we do get a tighter estimation of the pairwise difference in means. So I think overall, you're gaining by using this kind of design. So balanced incomplete block design. Here's the basic setup. We've got G treatments, but B blocks. And remember, B is presumably smaller than G. I'm sorry, K. K units per block. I messed up for a second there. K is smaller than G. B is the number of blocks, not the number of units per block. Each treatment is going to be replicated R times. So there's going to be B times K total units. Now, why is that again? B is the number of blocks, and then there's K units per blocks. So we will only be able to replicate as many units and blocks, or units within blocks that we have, and that's B times K. Well, we have G treatments and R replications of each treatment, so that necessitates that R times G must be equal to B times K, or else this isn't going to work for us. So you actually have to fashion your design so that this equality holds, so that B times K, the total number of units, is equal to R times G, the number of replication time, the number of treatment levels. So again, another place where I used to go look at the back of design books to figure this out. Now I just use R. It's easy to do it that way. In addition, each pair of treatments occurs together in the same number of blocks. So this gives you a value for how many times each pair, like the A and B pair or A and C pair, occurs in the same number of blocks. So it gives us that sense of the replication of the treatment pairs also. So let's look at these values in particular for an applied example. What if we have a balanced incomplete block design and we arrange our levels A and B and C? So notice we have 3 treatment levels G, and those are denoted A, B, and C. We arrange it this way versus that way. So take note, for example, thinking about the eye drop example. If these are all people, these blocks are each a person, and so you get 2 eyes on each person. This one would mean the person got type A in one eye and B in the other. A in one eye, C in the other. C and then B. And here they got AB, AB, CC. So both have G equal 3. K here, what is K again? The number of units per block. That's the number of eyes if we're thinking very concretely. So K is 2. R is 2 in this case because we have each level replicated 2 times across the whole experiment. And B here is 3. And what is B again? It's our number of blocks. So let's check. R times G is 6, which is equal to K times B, also 6. So the left side is a good balanced incomplete block design. Oops, I didn't mean to do that. But the right side is not. Can you think of what's wrong on the right-hand side? Well, think about replication of the treatment pairs, this idea of the pair of treatments occurring in the same number of blocks here. Here we get AB, one treatment pair occurring in a block, AC appearing in a block, and BC appearing in a block. And if we do that ratio of R times K minus 1 over G minus 1, that's this lambda here. So R times K minus 1 divided by G minus 1, that actually is 1, right? We get R times K minus 1, which is 1, divided by G minus 1, which is 2. So we get 2 over 2, which is 1. Here, we do not get all of the pairs replicated. In fact, we get AB, AB 2 times and nothing else. So not a balanced and complete block. If we don't get a whole number for lambda, like before on this design we got lambda equals 1, right? If we don't get a whole number, then there is no balanced and complete block design for that set of parameters. So you either need to like increase your number of blocks or do something else. Change your number of levels if possible, but you've got to adjust your design. Treatments can have a factorial structure. We won't really talk about that case, but it's easy to extend, of course. It is balanced in the sense that for estimating these effect size differences, it doesn't depend on I and J, okay? So we've got a general good estimate of the overall variance associated or error variance associated with the model. So a balanced and complete design always exists for any K less than G pair. Simply take all the combinations. You can get tables for smaller values of B and R. It can get a little tricky, or you can get R to help you also. It's been a very long time since I've done anything like this. This was more the work I did at an agricultural land grant based institution, not as common here. So we randomize by randomly assigning treatments to our treatment numbers, and then you just assign the treatment numbers to units within the blocks. Okay, so the randomization, remember, you just have to keep into account the blocking pattern that you get kind of dictated to you to ensure that you have a true balanced and complete block design. Here's the model for a balanced and complete block design. In randomized complete block designs, we did it both ways. Blocks could be fixed or random, but for balanced and complete, it's going to matter if we assume fixed or random. Okay, if they're fixed, then we get intra-block analysis, and all estimates are based on differences from within the blocks. Okay. This kind of complicates, I think, a little bit of the inferences because everything depends on the block inherently, or is within block estimators. If we assume the blocks instead are random, then there is information about the treatments in block totals. And so this leads to using what we call interblock recovery analysis instead. Again, I don't really remember, I barely remember this part of the class when I was in graduate school, but I think we did everything as intra-block analysis. I'd have to look back at my notes to know for sure, but generally now I would use the random approach, intra-block recovery analysis, so I'll emphasize that in class. So what intra-block recovery does is it gives you estimates for the cases where your blocks are random. It used to be hard, but in using Limmer in R, it's not too hard anymore. So we'll go over this in class. Pardon me. And we'll stop there for now.